to some of the more exotic holonomies, besides the ones that are strictly complex, although the first part of the lecture will be about something that's hyper-complex, extremely complex. And if there's time at the end, depending on how things go, I may actually start talking about the G2 and spin 7 cases, but we'll see how that goes. So yesterday we spent a lot of time talking about sort of what's known in the Kähler case and the Calabi-Yau case. That's those guys there. And today I want to switch down to something that a subgroup of this guy, what I'll call the symplectic unitary case, SPM. And I'm going to skip over this guy, which may look, there's a lot of parallels between the unitary and the special unitary, and what's called the quaternion Kähler and what's called the hyperkähler case. In each case, basically, you're adding you're taking a large simple group and adding on, in this case, a circle action, that is the unit complex numbers as multipliers, and in here you're adding the unit quaternions as multipliers. And so you might think it would make more sense to, since we had done unitary and then special unitary, it would make more sense to do quaternion Kähler and then hyperkähler. But actually, it turns out it's better to sort of skip over this and back up, as you'll see when I get to when I back up to this guy. So I'm going to go straight to the symplectic unitary case, and that'll leave only these two lonely guys that show up only in one dimension each to discuss for the final part of my lectures. So the symplectic unitary holonomy case, that's the case I want to talk about now. This is a subgroup, the subgroup of rotations that preserves a complex symplectic form and a complex and a Kähler form associated to that complex structure. If you notice that if you take the nth power of this complex symplectic form and divide by m factorial, you'll get the wedge product of the dz's, which is, of course, the wedge product of the dz's is the holomorphic volume form. So in particular, anything that preserves these two forms preserves the holomorphic volume form. So this guy is a subgroup of SU. Sorry, that should be 2m there, not 2n. So these guys are going to be, in particular, Kähler manifolds, Ricci-flat Kähler manifolds, and in fact, they'll have underlying preserving these guys is preserving this guy. It's going to be sort of like a refinement of Calabi-Yau structures. Now, the only time it's not a proper refinement is when m is 1, because it turns out that in m is 1, of course, when m is 1, there aren't any of these terms, and this is the volume form. So SP1 is the same as SU2 when m is 1, in 4 dimensions. But in all the higher cases, it turns out that this guy is a proper subgroup. In fact, SPM is a compact simple Lie group. It's a maximal compact subgroup of the complex symplectic group, and in fact, it's the intersection of the complex symplectic group with the unitary group. So that's why I'm calling it the symplectic unitary group. And preserving these forms is enough to define the group as a subgroup of all the general linear transformations. This is in case you're more familiar with the classification in terms of types, like type A, B, C. This is the compact form of type C. It's of the simple Lie groups of type C. Its rank is m. Its dimension is 2m squared plus m, and it acts irreducibly on R4m, which you think of as C2m. And and moreover, in fact, it acts transitively on the unit sphere. Now, there's a different way to think about it, one that doesn't particularly privilege the complex structure that we have, and reveals more of the kind of the geometry that's going on behind SPM, and that is the following thing. If you now split the complex symplectic form into its real and imaginary parts, if you look at it, you'll notice that, and for indicial symmetry, we'll rename omega to omega 1, little omega to omega 1, then each one of these forms is a non-degenerate 2 form on R2M. And, in fact, even though they look like they came from very different places, they all pretty much look, they're almost all interchangeable. In fact, if you do this, because each of these forms is non-degenerate, that means that, for example, using omega 1 and omega 3, there's a unique map J2 that takes such that when you plug it into here, this equation holds. There's a unique map J3 such that when you plug it into here, this equation holds. And there's a unique map J1 such that when you plug it into here, this equation holds. All that uses is that these guys are non-degenerate. Omega 1, omega 2, omega 3 is non-degenerate. That's enough to give this, to define these three maps. And if you have trouble remembering these formulas, just remember the first one and then cyclically permute 1, 2, 3, and that's how you get the others. This symmetry is not just done just accidental, and in fact, if you go through and look at the definitions, go back on the first page and look at how we split it out into its components, you'll find out that each one of these J's is a complex structure of its own. Ji squared is minus 1. They skew commute. That is, when ijk is an even permutation of 1, 2, 3, jij is minus jji and is minus jk. The minus is there for, the minus is there because it's true, for one thing, and you might wonder why I don't just switch the signs of all the j's to make it so that I can make I times j be k, but there's a good reason for that. It turns out that the quaternions, which these things are trying to generate, the quaternions aren't commutative, as you can see from this, and when you look at quaternion vector spaces, you want to be able to distinguish right quaternion vector spaces from left quaternion vector spaces. And it turns out that when you're working with right quaternion vector spaces, you want the multiplication here to be jij is minus jk. And it turns out that right quaternion vector space is the right thing to deal with here. That's a minor point, but it probably won't matter that much. But I just to make sure that you knew that I deliberately put that minus there. It's not a typo. And moreover, if you now use each one of these almost complex structures, these complex structure maps on the vector space, to plug it into omega I itself, remember J2 came from comparing omega 1 and omega 3, but now if you plug it into omega 2, for example, you'll get, it turns out, a quadratic form, a symmetric quadratic form, and in fact all of these are equal. So so the J1, J2, J3, not only are they each individually complex structures, but orthogonal complex structures, they skew commute, but they all basically, when you apply them to their corresponding, what would be Kähler form, give you the same metric. And so if you think of using the J's as defining how to multiply by I, J, and K in Rm, that makes this into a vector space over the quaternions. In fact, a right vector space over the quaternions. And and in fact, you see that this group SPM is in fact the set of quaternion linear orthogonal transformations of HM thought of as a vector space. So that explains why they're all more or less all three forms are more or less all on the same footing and should be thought of that way. And so we'll make a definition. We'll say that a triple of non-degenerate three forms, eta 1, eta 2, eta 3, on a real vector space is a hyperunitary structure if, when you use them to define the maps J1, J2, J3 by these formulas, they are almost complex structure. They are complex structures. They skew commute. They satisfy these, and moreover, they define a positive definite inner product that all agree. That's a lot to ask, it seems, and you'll be gratified to know that once you fix the dimension, first of all, if a vector space has a hyperunitary structure, its dimension has to be divisible by 4. I'm always assuming V is finite dimensional, by the way. I should have said that. A real finite dimensional vector space. Then the dimension is always divisible by 4. And moreover, once you fix the dimension, all the different possible hyperunitary structures are actually isomorphic. That is, if you had two different hyperunitary structures, there's an isomorphism of V with itself that lines them up. So there's not any local invariance or algebraic invariance or anything like that. But it does seem to be a very delicate kind of highly overdetermined structure that, and it seems, when you first look at it, it looks kind of unlikely that such a thing would really exist, or at least exist on manifolds. I mean, certainly on a flat vector space you can define such a thing, but then can we actually get one to curve around, and can we get a metric whose holonomy preserves such a structure? Well, we can go ahead and define such a thing. Suppose now that we have, and let's investigate their properties. Suppose now that we have a manifold of dimension 4m whose holonomy is conjugate to a subgroup of SPM. Not necessarily all of SPM, but just possibly some proper subgroup. Again, applying the holonomy principle, we know that there will be defined 3 non-degenerate 2 forms that are parallel with respect to the metric, and such that at every point they define a hyperunitary structure on the tangent space. That's just applying the holonomy principle to this fact that SPM is the stabilizer of a hyperunitary structure. And of course, because they're parallel, the forms are closed. And in fact, from the very definitions, because we know that each of the J's is now each of the J's associated to the omegas, since they're constructed out of G, which is obviously parallel with respect to itself, they're parallel. So each one of these guys is Kähler. So we have a priori 3 different Kähler structures we could define on the same for the same metric. But even that understates what's really true, which is that, in fact, if you take any linear combination of the J's, where the coefficients, sum of the squares is 1, and the corresponding omega, then that guy is Kähler. So in fact, there's a whole 2-sphere of Kähler structures that all have the same underlying metric. And because G is Kähler in so many different ways, we say it's hyper-Kähler. And I mean, roughly speaking, that's the etymology of the term. So, well, so what about? So we know now that we get, if we could find such a holonomy, then we'd have this kind of hyper-Kähler structure. And what shouldn't be too surprising, given what we've said so far about the unitary and special unitary cases being characterized by closed forms being parallel, by taking closed forms, getting associated metric, and then noting that the corresponding forms that you started with were parallel with respect to that metric. The same thing is true in this case. That is, suppose that you have a manifold that has a triple of closed, it's important, closed 2 forms, such that at each point they define a hyperunitary structure. then we know that there is an underlying compatible metric that's part of the definition of hyperunitary structure. And now the conclusion is that those forms are actually parallel with respect to that associated metric. And in particular, since the parallel translation has to preserve those guys, that means that the holonomy has to be a subgroup of their stabilizer, which is SPM. So if we can find a triple of closed forms that define this hyperunitary structure, then we'll have a metric whose holonomy is a subgroup of SPM. Well, and as usual, when we prove this, we'll basically get a local normal form, and we'll hopefully see how many such things there are. So that's our goal. So I'll give a sketch of the proof, as I've been doing in the other cases. By the algebraic properties, by the very definition of it being a hyperunitary triple, we know that the dimension is 4m for some m. And moreover, if you now take omega 2 plus I omega 3, this is now a complex valued 2 form. And if you take its top exterior power and normalize it, divide by m factorial, this guy will be a complex 2m form that's decomposable as a complex valued form, and its wedge product with its conjugate's not 0. And it's closed. And so we're now in the same situation we were in the Calabi-Yau case. We have a closed, decomposable form that defines a almost complex structure, and by quoting that argument that we gave already, we know that this guy is actually a holomorphic volume form for some unique integrable complex structure J. And in fact, if you go back and look at the way the algebra was constructed, this J is J1, because this guy is actually complex with respect to, is of type 2-0 with respect to J1, and therefore upsilon will be of type 2m0 with respect to J1, and that uniquely determines J to be J1. And so that says in particular that J1 has to be integrable. Of course, if I were to repeat this argument with, say, omega 3 plus I omega 1, then I would conclude that J2 is integrable. And with omega 1 plus I omega 2, I'd conclude that J3 was integrable. So you get all those, each one of those guys is integrable, although I'm not going to directly use that. Now, the form capital Omega itself is of type 2-0 with respect to the complex structure J, and it's closed. So it's, in particular, it's holomorphic with respect to that underlying complex structure. Now, we're now in the holomorphic category. We have a holomorphic symplectic form on a complex manifold, and the Darboux theorem, which says that if you have a closed, non-degenerate 2 form, it can always be put in a standard form in local coordinates. The Darboux theorem is also true in the holomorphic category, just like it's true in the real category. And so we just apply the holomorphic Darboux theorem, and we see that there are coordinates that every point of M lies in a coordinate neighborhood for which there are coordinates, so that this form looks like this in those coordinates. Now, you may notice that I have switched around the indices a little bit. Instead of being DZ1, DZ2, DZ3, DZ4, I've run the leading guys first and then the following guys. The reason for that is that it simplifies a matrix later on. It's just a renaming, so don't worry too much about that. Anyway, so there are holomorphic coordinates. Omega looks like this. And we know that little omega 1 is a Kähler form for this complex structure that's defined by Z. So we can quote what we know about Kähler things. We know that there is a function, locally at least. We may have to shrink U a bit to get such an F, but there is an F, so that omega 1 pulled back to U is it looks like this, and the associated metric looks like this, where the Hessian matrix of F, the complex Hessian matrix, is positive definite. That's just from this fact that this is a Kähler metric. Now, there's one thing left that we have to worry about here, which is that we're not quite done, because if we just start on C2M and choose a function so that this is positive, so this guy is positive, we'll get a Kähler metric, but it's not clear that this omega 1, together with the real and imaginary parts of this, will be a hyperunitary structure. That's a condition that we still have to impose, and we don't have that yet. I mean, we've gone a long ways, but we still have to get it to be hyperunitary. So, so we have to impose that condition, that omega 1 and the real and imaginary parts of omega 2 of the holomorphic symplectic form that we wrote down define a hyperunitary structure. Now, that turns out to be a lot more equations than just one. In the when we were imposing the condition back in the Calabi-Yau case that the volume form associated to the symplectic form was a constant multiple of the volume form associated to the holomorphic volume form, that turned out to be a single equation on F, that Monge-Ampère equation. But now, getting this guy to be compatible with these guys is more equations. In fact, it turns out to be the following system of equations. That is, what you do is you take the complex Hessian matrix and its transpose, you apply them to this skew-symmetric matrix, and you better get the same skew-symmetric matrix back. That's what the equation is. Now, if you count up how many independent equations this is on the Hessian matrix, it turns out that it's 2m squared minus m second-order nonlinear equations on F. It's 2m squared minus m equations on this Hessian matrix. I mean, it looks like it's more, but most of those equations are degenerate. Most of those equations are actually dependent on each other. There's exactly 2m squared minus m of them that are independent. But they're all equations. There are a bunch of different equations on this single function, f. And, in fact, you can recover the Monge-Ampère equation that we had, which was the determinant of this guy is 1 by taking determinants of both sides of this equation. And you'll see that the determinant of h, you'll get the determinant of h is plus or minus 1, but we know h is positive definite, so the determinant's plus 1. So what we've got so far is we've seen that we can choose that if we have such a guy, if we have such a hyperkähler structure, we can always choose coordinates to put two of the two forms in a standard form with constant coefficients. And then the third comes up in terms of one arbitrary function. That arbitrary function has to satisfy an inequality. To its Hessian complex matrix has to be positive definite, and then it has to satisfy a bunch of equations. I'll talk a little bit more about those equations in a minute, but let me come down to sort of finish the argument, is that conversely, if you choose a function on an open set in C2M, and suppose that it satisfies this set of equations here, that its complex Hessian satisfies that equation, and the Hessian is positive definite, then when you write down this metric, then the corresponding omega 1 that we wrote down on the previous slide, and capital omega, which was the constant coefficient thing that we wrote down on the previous slide. Those guys are all parallel with respect to this metric. You can prove this just by the easy way to do it is to choose your coordinates carefully, choose your holomorphic coordinates carefully, and you can make sure that all of the third derivatives of f are 0, and that's enough to show that g, the first derivatives of g in that coordinate system at a point are all 0. So and the first derivatives of this guy and this guy at that point are all 0. So that implies that they're parallel. It's that same point that we made in the Calabi-Yau case. It's a elementary calculation, just being careful about how you choose local coordinates. So we're reduced to studying this equation here if we want to understand what the local hypercalometrics look like. Now, unfortunately, this system of equations, well, it is elliptic because it contains an elliptic equation. You know that if you just take the determinant of both sides, you'll get the positive definite Monge-Ampere equation, which is elliptic. So it's an elliptic system. It's elliptic overdetermined, unfortunately, and the sort of standard PDE methods don't tell you a whole lot about it, unfortunately. However, there's a good set of techniques for dealing with overdetermined systems of equations, particularly ones that have a large symmetry group like this one clearly does, and which unfortunately I don't have time to describe completely for you today, but I'll tell you what the result is when you apply this theory. The technique that allows you to study these overdetermined systems of equations asks whether or not the equations are compatible with each other in a certain sense, and the technical word is involutive. And it turns out that this system of equations is involutive. It satisfies the conditions needed to apply the Cartan-Taylor theorem, which unfortunately, again, that's another series of lectures to talk about that. But the basic upshot is this: that if you want to understand the local solvability of this equation, of this system of equations, you can set it up not as a Cauchy problem, as a single Cauchy problem, but as a sequence of Cauchy problems, where you start with initial data in some dimension. Start with initial data in some dimension, and then solve one Cauchy problem to thicken up to the next dimension. Take that as initial data to thicken up to go one dimension higher. Take that as initial data to thicken up one dimension higher, and keep going. And because the equations work well together, they're involutive. All these thickenings are compatible with each other, and you finally wind up with at the last step, you solve a single initial value problem that gives you a solution defined on an entire open set. And it turns out, again, to really go into this, I'd have to really give the whole story. But for solving this system of equations, what you do is, it turns out that basically what you start out with is essentially arbitrary initial data. You get to choose 2m arbitrary functions on a submanifold of C2m that has 2m plus 1 real dimensions. That's basically what you get to do. So it's slightly more than half the dimension of the ambient space that you're working in. Now, when m is 1, that's 2m functions of 3 variables. It's actually defining things on a hypersurface. This is the case that we already saw in the Calabi-Yau case. That is, that you give the initial data on a hypersurface, and also in case m equals 1, there's only one equation. And so you can solve it. But as m increases, the amount of initial data you get to prescribe only goes up half as fast as the dimension. So you have to start earlier and start applying this Cartan-Kähler machinery to thicken things up to get a solution. But the end result, once you understand what's going on, is that there are lots of solutions to these equations, and they depend on, you get to basically choose 2m arbitrary functions of 2m plus 1 variables. 2m plus 1 real variables. I'm not going to go into details about it, but one of the things that comes out when you look at what the general solution looks like is that you can immediately tell that you can specify the initial data so that the curvature, the value of the curvature tensor at a point, fills out the entire SPM. So the generic such metric has holonomy equal to SPM. There's no so the conclusion is that these guys do exist locally, and there are lots of them, hyperkähler metrics that are not products of lower dimensional things and don't have holonomy, some subgroup of SPM, but they're the only things they have parallel are those three forms: omega 1, omega 2, omega 3, and the algebra that they generate. One thing that you'll notice is that, again, because SPM is a subgroup of SUM, these guys are Ricci flat, because of course anything with holonomy in SUM is Ricci flat. In particular, that implies that these metrics are real analytic in some local coordinate system, but we already knew that from the local picture, because we knew that F already satisfied at least one elliptic equation, namely the Monge-Ampere equation, and that was enough to force real analyticity. A very interesting feature about these guys is that the associated Riemannian manifold has a whole lot of different calibrations. In fact, for every one of these Kähler forms, omega lambda that I was writing out before, you can take its normalized pth power, and that'll calibrate something. That'll calibrate the two p real dimensional submanifolds that are Kähler with respect to J lambda. And you've got this whole two-sphere of J's that you can work with. So there's lots and lots of different calibrated guys. Also, if you take the holomorphic volume form associated with J lambda that's parallel, call that upsilon lambda, and take its real part, or imaginary part, or in fact multiply by any constant phase factor, those guys are all calibrations. And so this manifold here is filled with lots of different varieties of calibrated submanifolds. There's just lots and lots of minimizers locally in all these guys. Important thing I'll just remind you, again, one of the basic local properties is that if you have a hyperkähler guy, then taking the complex, then using this as your symplectic form, you actually get a holomorphic symplectic manifold. In other words, you can get something that lies entirely in the holomorphic category that doesn't refer to metrics at all, and that's an important thing for trying to understand what for trying to understand global properties, which is the thing I want to talk about next. So global examples. So we now know that locally there are lots of these things. They're very flexible, but there's a question about whether or not there's any good global examples. For example, are there complete examples? Are there compact examples? And again, Calabi came to the rescue and produced the first complete examples that were known. But one thing that wouldn't work, is to look for a rotationally invariant example on C2M, like we did for the SUN case, because we already know that that reduces to an ODE for a single function, and we saw that the solutions to that equation all give you holonomy with SU2M, not SPM. So starting with trying to do the naive thing that we tried for SPM is not going to work. However, even though C2M won't work, looking for something rotationally invariant on C2M, there's another manifold to work with that has a natural symplectic structure on it, that has a large symmetry group, and we can look for solutions that are invariant under that large symmetry group and hope that we can reduce to an ODE again. And one, in some sense, if you're familiar with complex geometry, if you're familiar with symplectic geometry, then you know that a very natural class of symplectic manifolds are the cotangent bundles. Every cotangent bundle of a smooth manifold has a smooth symplectic structure, and that's also true in the holomorphic category. Every holomorphic cotangent bundle of a holomorphic manifold has a holomorphic symplectic structure, a canonical one. And if you choose a manifold that's very, very symmetric, has lots of symmetries, all those symmetries will, of course, lift up to the cotangent bundle, and you'll get a symplectic manifold, a holomorphic symplectic manifold with a lot of symmetry. And so a natural one is to take the complex projective space. And in fact, there's another reason that you'd want to take complex projective space that makes it particularly good for this, is that CPM is, of course, it's a Riemannian symmetric space of SU m plus 1. In fact, there's a unique Kähler metric on this guy that's invariant under SU m plus 1. And that action extends to the cotangent bundle of CPM. And because CPM is rank 1, and I'll say a little bit more about that in a minute, because it has this rank 1 property, SU m plus 1, while it doesn't act transitively on this guy, it acts with orbits of codimension 1. Now, what does rank 1 mean? In our situation, what rank 1 means is that not only does the isometry group act transitively on the manifold, but it acts almost transitively on the tangent bundle. That is, if you have two vectors, maybe based at different points, that have the same length in the induced metric, then there's an isometry that carries the one vector to the other. So, and since the tangent bundle and the cotangent bundle are naturally dual, that means that it acts the same way on the cotangent bundle. That is, if you have two covectors, that is, one forms, even based at different points, the isometry group of CPM, if they have the same length, you can take one to the other. So what that means is that the orbits of SU m plus 1 acting on the cotangent bundle are of codimension 1. They're the level sets of the length function. There's the zero level set, which is, of course, the zero section. That's a small orbit, but all the other orbits are codimension 1. They're hypersurfaces. So that means, in particular, that that the level sets are cut out by a single function. The orbits are cut out by a single function, which I'll call is sort of the radius, the norm, the square norm of cotangent vectors on CPM. So that suggests doing the following thing. So, and this is Calabi's idea, what we do is we look for a hyperkähler structure on this guy of this form where the symplectic form, where the omega 2 plus I omega 3 is the canonical holomorphic structure on CPM, on the cotangent bundle of CPM, and where omega 1 is I dd bar of a function of rho only. So this would be a solution. This would be a hyperkähler structure that has a very large symmetry group. In fact, we have basically a function of a single variable is parameterizing these things. And we just ask, what's the differential equation that f would have to satisfy in order to make this actually be a hyperkähler structure? Well, I don't want to spoil your fun. You should have something to do. Exercise is to write down what that differential equation is for f and check that you can integrate it. And sure enough, there is such a function, and you can write down explicitly what the formula is, and you get this explicit hyperkähler structure on the cotangent bundle of CPM. And not only that, once you get the formula for f, you can see immediately that the resulting metric on the associated metric on this guy is complete. Its symmetry group is exactly SUM plus 1. So actually, it's SUM plus 1 plus multiplication by e to the I theta in the fibers there. It's slightly larger than SUM plus 1. And that was the first known complete example. So actually, this analysis, this construction of the example was done by Calabi before the local analysis was done. So at the time that Calabi did this, he produced this example. It was the first known example of a metric with holonomy SPM, non-trivial example. It's now known that there are lots of these guys. Let me say, that's odd. Did I? Okay. That's a little glitch in my display program. We'll see whether or not the glitch shows up at the other end. As far as constructing compact examples, of course, those examples aren't compact. And in fact, it turns out Calabi's examples are very homogeneous. They're as homogeneous as you can get. It turns out that you cannot construct a metric with holonomy SPM that's actually homogeneous. And the short reason for this is that there are no homogeneous metrics that are Ricci flat, and these guys would all be Ricci flat. But you can get cohomogeneity 1, which is, for example, the Calabi's example. So there can't be homogeneous examples. But it turns out that even worse, if you look for a compact example with holonomy SPM, you can show that thing. Again, because it's a Ricci flat Calabi-Yau guy in particular, it cannot have any continuous symmetries either. So the symmetry group, the most you could have is discrete symmetries. And so there's not going to be any sort of obvious reduction method that would allow you to reduce the problem to some lower dimensional thing by dimensional reduction. So compact examples have to be constructed by some other method. And fortunately, though, it turns out that the Yau's solution of the Calabi conjecture, well, the solution of the Calabi conjecture basically hands it to you without a whole lot more work. If you take a hyperkähler structure, so a hyperkähler structure is a Kähler manifold that has a parallel holomorphic symplectic form. That's what we've been talking about. And it's not too difficult to show that, in fact, if you have any, starting with something like this, if you have any holomorphic P form on the M, and M is compact, then phi has to also be G parallel. And the reason this equation is a little bit allegorical because I haven't defined all the terms in it, but and I also see that I've got that's okay. Right. It's also G parallel, and the reason is basically this: that you can write down a Weizenbach type formula that says that if you take what's called the rough Laplacian, that is, you compute nabla of of phi, and then its adjoint applied to phi, where phi is a p0 form, then that's expressible as basically the d bar operator and its adjoint plus a Ricci term. Ricci acting on phi in some way that I have not specified. Right? The Ricci curvature acting on phi in some way. But Ricci is 0 if the holonomy is SPM, so that term's not there. So if you have a holomorphic p form, then this term's 0, and you see that phi is in the kernel of the rough Laplacian, which forces it to be, on a compact manifold, forces it to be in the kernel of the covariant derivative, which means it's parallel. So, so any more holomorphic p forms would, if you had any more holomorphic p forms on M, they'd be parallel. And because SPM doesn't preserve any holomorphic forms other than omega and its powers, if there were any more holomorphic p forms, the holonomy cannot be all of SPM. So what we need then is something. What we need then is a complex manifold, and here's what the proposition says. If you have a simply connected compact complex manifold, suppose it has a Kähler metric, and its algebra of holomorphic forms is generated by a holomorphic symplectic form. That is, all the holomorphic forms are the powers of a single symplectic form. Then this manifold has a Kähler structure so that this guy is hyperkähler. And moreover, the associated metric has holonomy equal to SPM. So no subgroup. And let's look at the reason. What you do, the first step is we know we have a holomorphic volume form because by hypothesis we have this, and by Yau's theorem that means that there is a and we're also assuming that it has a Kähler metric. So we can apply Yau's theorem to this, and and that implies that there is an omega 1, a Kähler form with respect to the underlying complex structure of this form, a constant times the thing we started with plus I d bar f, so that this is a Calabi-Yau structure. Now, by the argument that we gave in the Calabi-Yau case, once you get to this stage, this guy is Ricci flat. I mean, the underlying metric is Ricci flat, and by the argument that we gave on the previous page, that says that this holomorphic form has to be parallel for the underlying metric. So that means the holonomy is a subgroup of SPM. Now, if the holonomy acts irreducibly, just look at Berger's list. There's only one. There are no proper subgroups of SPM on the list. And so if the holonomy acts irreducibly, then the holonomy has to be all of SPM. There's no way around it. On the other hand, if the holonomy were to act reducibly, if you look at look at the classification theorem, what are the possible subgroups, even allowed to be products, that can fit inside SPM? And they're all like this. They're products of SPMs, basically, plus flat factors if necessary. But the flat factors would themselves cause there to be, would themselves cause there to be other parallel holomorphic forms. And in fact, see, but if the holonomy is reducible like this, then by the de Rham theorem, this thing would split, and we'd have it's a product of complex manifolds, each one of which carries a holomorphic 2 form. And now, if k is bigger than 1, we'll have a whole bunch of non-zero holomorphic 2 forms, but that would contradict our hypothesis that the only holomorphic 2 forms are the multiples of omega. So that means k has to be 1, so that means the holonomy has to act irreducibly. And by the classification theorem, has to be SPM. So this reduces the problem to something manageable. I mean, something we can hand to our algebraic geometry friends and say, go out and find this for me. Find me a compact Kähler manifold whose holomorphic forms are generated by a symplectic form. And, well, at one time, people went and asked the algebraic geometers to do such a thing, and nobody knew one. And in fact, for a short time, there was a purported argument that claimed that no such thing could exist, except in the m=1 case, which we already know is issue 2 anyway. But eventually, it was found that that purported argument had a hole in it, a serious hole, and some examples were constructed. We now know that there are quite a lot of these compact Kähler manifolds whose holomorphic forms are generated by a single guy. Here's the first and probably best known example. If you start with a K3 surface, that is a complex surface that has a metric with holonomy SU2, which is the same as SP1, remember. So it has a parallel 2 form, holomorphic 2 form on it, which is its volume form. What you can do is take the product of this guy with itself m times and divide by the symmetric group acting as permutations on this guy. That's what they call the symmetric product. Call that Y. Now that's a singular manifold, unfortunately. But it's possible to resolve those singularities in a particularly nice way that doesn't mess up the symplectic structure. See, if you take a product of symplectic manifolds, then you can get then that is a symplectic manifold, because you just add up the pullbacks of the symplectic forms on each of these guys. You get a symplectic form that's invariant under this permutation group acting. It pushes down to Ym. Unfortunately, Ym is singular, but if you resolve it carefully, and I don't have time to go into details for that, if you resolve it carefully, then you can do it in such a way that you still get a symplectic form. And computing the not only is it symplectic, but it's Kähler, and using the Hodge theorem, you can actually compute what the holomorphic forms are, and it turns out there's only one. It's the symplectic form that survived, and so there's an example. And so we know that there is a metric with holonomy SPM on this guy. Of course, nobody has any idea what it is. I mean, nobody can write it down. I mean, we can't write down the metric on K3, but we know it's there. So they do exist. In the last few minutes, I want to do what everybody does is give lip service to the quaternionic Kähler case. That is, I'm not going to go into a whole lot of detail about it, because in fact, basically what I'm going to do is reduce it to the hyperkähler case in a sense. So I now want to sort of back up and look at the case where the holonomy is SPM SP1. And we'll talk about quaternionic Kähler holonomy. So I need to first of all tell you what this SPM SP1 is. Now, because J1, J2, and J3 don't commute, they don't belong to SPM, because SPM is the set of things that commute with them, and so they don't belong to it. But instead, they generate their own little SP1 subgroup. That is, if you look at the set of combinations of them of unit size, there's a 3-sphere of them like this. This group of linear transformations is closed under multiplication and inverse, so it's a subgroup of SO4M. It's the set of things. It's the set of orthogonal transformations that commute with SPM. It's exactly the commutator subgroup. The two of them together, they intersect in one thing. They intersect in minus the identity. Well, two things, plus the identity and minus the identity. They intersect in two things, but they generate this group, which I'll just denote SPM, SP1, sitting as a subgroup of SO4M. This is a maximal subgroup of SO4M, by the way. There's nothing between it and SO4M. In particular, it's not a subgroup of any unitary group. In fact, this group, it doesn't leave the two forms invariant, but it does leave invariant the sum of their squares. And I put the 1/6 there because I want this guy to have want this guy to be a calibration. And the 1/6 is what makes it have comass 1. And conversely, as long as m is, well, when m is 1, this is a 4 form. Well, this is always a 4 form. But when m is 1, this is just the volume form in dimension 4. And the set of linear transformations preserving the volume form is SL4R. But when m is bigger than 1, this 4 form actually is enough to define SP1, SPM, SP1. That is, the group of linear transformations that preserve it is exactly SPM, SP1. It's again a kind of linear algebra thing. And so that leads us to make a definition. A 4 form on a vector space of dimension 4m will be said to be a quaternionic 4 form if it's equivalent to this under some linear isomorphism between these two. The set of quaternionic forms is a homogeneous space. It's GL4MR modulo this group here. And from that you can work out what its dimension is. It's some not, unfortunately, not an open set in this set of 4 forms, but it's a algebraically defined subset. Before I say what I'm going to say about the quaternion-Kähler case, I want to point out that if you look at the difference for the possibilities for curvature here, the curvature of a quaternion of a hyper-Kähler manifold is irreducible. There's no Ricci piece. This stuff is actually an irreducible representation of SPM. This notation, by the way, means polynomials of degree, complex polynomials of degree 4 on C2M, and it turns out that as a representation of SPM, that admits a certain natural conjugation. So you look at the real things in that vector space, and that's the vector space we're looking at. That's the space of curvature tensors, and you'll notice that if you look at the holonomy, this guy, the curvature tensors don't get that much larger. They pick up a single factor of r. In particular, they don't pick up anything corresponding to the traceless Ricci curvature, and an immediate consequence of that is that the curvature of these guys, I mean, the traceless Ricci for such a thing is 0. So if these things exist at all, they're Einstein. That is, you have a scalar curvature, scalar curvature, and that's got to be, that's the only thing that survives in the Ricci tensor. And so I just want to run through a few properties that the thing has. Suppose now we have a 4M manifold. M's always bigger than 1 now. Endowed with a quaternionic form phi, and in other words, it induces it's a quaternionic form on each tangent space, and let G be the associated metric. This is so here's a set of things that you can prove without too much trouble. First of all, if phi is parallel with respect to G, then G is Einstein, because G will have holonomy SPM SP1, and we already saw that the only thing that survives of the Ricci tensor is the multiple that is the traceless part, which it forces it to be Einstein. In particular, the scalar curvature is constant. As long as the scalar curvature is not 0, the holonomy will be, and that shouldn't be a times, that should be a dot, and there's also a slight error. It should say if the scalar curvature is not 0, the holonomy is this, or it's a locally symmetric metric. There are every one of the compact simple Lie groups has a Riemannian symmetric space that is quaternion-Kähler. And they have holonomy below SPM, SP1, but that's the only other possibility if the scalar curvature is not 0. I should have put that in there. So there should be or G is locally symmetric. If the scalar curvature is 0, that is, if the curvature doesn't take advantage of that little R piece that lies out there, then in fact the holonomy is a subgroup of SPM, and you're down in the hyperkähler case. So we might as well consider only the case where the scalar curvature is not 0, because we've already treated the hyperkähler case. The corresponding statement of, in the Calabi-Yau case and the hyperkähler case, we were able to show that getting the metric to be getting them to be parallel with respect to the corresponding metric, it was enough to have them be closed. That's essentially true in the quaternion-Kähler case, except that you have to skip the two-dimensional case. As soon as the dimension is bigger than 2, the closure of this 4 form, of the quaternionic form, implies that it's parallel with respect to G. And more or less for the same reasons, that it's just so many differential equations. The closure is so many differential equations that it kills all the torsion and forces the thing to be parallel. The m equals 2 case is interesting, but let me leave that aside for now. And here's the other reason that the quaternion-Kähler case doesn't get as much attention. It's because it turns out that if you do have something with holonomy SPM SP1, then this form can actually be constructed from a one higher dimension or higher hyperkähler structure in a canonical way. There's a natural way to take a hyperkähler structure like this with an S1 symmetry and sort of, if you know about reduction in the symplectic case and hyperkähler reduction, and then quaternion-Kähler reduction, which is, all those things, one follows after the other, then it's possible to show that everything like this comes from a hyperkähler structure in a natural way. And so basically we've figured these things out already. We just have to figure out what these things look like one dimension higher if you impose an S1 symmetry. And so you go through that analysis, one dimension higher, impose an S1 symmetry, and it turns out they balance each other out almost perfectly in that the general local metric depends on 2m functions of 2m plus 1 real variables. Just like the hyperkähler case, having that extra constant floating around just serves to confuse things. It doesn't really make things any more difficult or make things much more flexible. It has been proved, a combination of people, that every compact example with positive scalar curvature that's in quaternion dimensions 2 or 3 is actually a Riemannian symmetric space. So there's nothing like these examples that were constructed in these compact examples that were constructed by algebraic geometric methods in these low dimensions. And in fact, what's even more mysterious is that we don't know any compact examples with positive scalar curvature except the Riemannian symmetric ones. So far, I don't know whether people call it a conjecture or not, but there's a sort of a suspicion that maybe there aren't any compact examples with positive scalar curvature that aren't Riemannian symmetric spaces. On the other hand, if you give up it being a manifold and allow certain mild singularities, that is, if you allow orbifold singularities, then it turns out that there are lots of examples that have been constructed. There's this, the work of Galiski et al. We now know that there are lots and lots of things that have one singularity here, one singularity there, small sort of scars lying around, but otherwise complete. And maybe that's just the natural way for these guys, that we should be working in the orbifold category anyway. I mean, there's a lot of evidence. There's a lot of evidence that the reduced holonomy guys tend to like having singularities anyway, and so maybe we should just learn to live with that, as we'll see tomorrow when we look at the G2 and spin 7 cases. So there's all this has taken care of the classical cases. There's two more cases, lonely and sitting out there, to figure out whether or not they exist, what their properties are, and so forth. That's the G2 and spin 7 cases, and that's what I'll talk about tomorrow. Okay, thanks.